I'm making this video to walk you through my proof of the Pythagorean theorem that we covered in today's lesson. And we started by just drawing this right triangle, and I call it the general right triangle ABC. I've labeled the vertices A, B, and C. It's general because I haven't assigned any values to side lengths. I haven't assigned any values to angles. So it's not a specific right triangle. It's a very general right triangle. And I did label these two angles, the angle here and the angle here, to just indicate that they could be different. Of course, they sum to 90 degrees because this is a right triangle, but they could be just any value within that constraint. And then the next thing I did was I divided the triangle with segment AD, this segment right here, in a very specific way so that this is a right angle right here. In other words, and what I've stated over here is that CDA and ADB, these two angles, are both equal to 90 degrees and, of course, equal to each other. And so now there's a few things that we can do. Notice there are three triangles. There's the big triangle, and then there's the medium triangle, and then there's the small triangle. And I can first say that this angle right here, CAD, has got to be congruent to this angle CBA over here. And that's from the triangle angle sum theorem. And basically, if these two angles add up to 90 degrees, right? These two angles also have to add up to 90 degrees, so these two angles must be equal. And what that allows me to do is to use what we call angle-angle similarity to demonstrate that the big triangle is similar to the medium triangle. And what it means for two triangles to be similar is that they're the same shape, but they may be different sizes. And that's an important thing for our proof that is going to come up in a little bit. I can do a similar thing here and demonstrate that angle DAB, this angle, is congruent to this angle up here for the same reason, and that means that the triangle ABC, the big triangle, is also similar to triangle DBA, which is like the medium-sized triangle here. So what I have is, and I redrew it right here, I redrew these three triangles, and I've labeled their vertices, and I've just drawn them this way in order to sort of lay out my three similar triangles. And notice they're three triangles that are three different sizes, but because their angles are all equal, they're the same shape. And I made a note over here. These three triangles are similar, and what that means for the purposes of this proof is that the ratios of corresponding sides are equal. And so I continue by just looking at the first two triangles. And notice I could actually, what I've done right here is I've said that the ratio of side BC, which is the hypotenuse of the big triangle, divided by the longer leg, AB, right, is going to be equal to the same ratio from this second triangle. In other words, the hypotenuse AB divided by the long leg BD right here. So the ratio of these corresponding sides, hypotenuse and long leg, is equal to the ratio from this triangle, hypotenuse and long leg. And of all the ratios I could have constructed here, there's a specific reason why I chose the hypotenuse and the long leg. And the reason is because notice that the hypotenuse of this triangle is AB, and the long leg of this triangle is AB. And remember, if I go back to my original general triangle, I'm really trying to demonstrate the relationship between the three sides of the big triangle. So when I look at the medium triangle and the big triangle, they share this side AB. And so I want to relate everything back to the big triangle. So after composing this proportion, I can just use the multiplicative property or the property of equality, the multiplication property of equality, to rewrite it like this. And notice we get an AB squared out of that. And that's helpful and interesting because we know that we square, we end up with the side lengths squared in our final Pythagorean theorem. I'm going to look at the first triangle here, the big triangle, and the little triangle now. And what I'm choosing here is again the hypotenuse and the short side. Notice I said AC, the short side, divided by BC, the hypotenuse. And the reason I chose those two sides is because, look, the hypotenuse of our little triangle is AC, and you can see why in the original diagram, right? This is the short side of the big triangle, but it's also the hypotenuse of this little triangle. So when I construct this proportion and do a little algebra, I end up with an AC squared. And again, we like these squared terms because we know that our Pythagorean theorem has it involves the square of the side lengths. The last thing I need to pull is that if we go back to the original diagram, I get this relationship that BC is equal to BD plus DC. And here's what that really means. It means that the length of this hypotenuse of the big triangle is just the sum of these two sides, CD and DB. I rearranged my letters a little bit, but it's these two sides. And so I can rearrange this just a little bit and solve for DC. And the reason I want to do that is I can substitute it in for this DC, and I end up with this relationship. And notice now, after using the distributive property, I get AC squared equals BC squared minus the product of these two sides. And going back to my relationship over here, notice that I have a BC times BD here. And also from this proportion, I had a BC times a BD, and that was equal to this AB squared. So again, let's substitute that AB squared right in here, right here for this thing. And that's pretty much it. We're done. I rearrange it a little bit to get the hypotenuse all by itself over here by adding the AB to this side. And notice AB squared plus AC squared equals BC squared. And going back to my original triangle, AB squared, leg number 1 squared, plus AC squared, leg number 2 squared, is equal to the hypotenuse squared. And so that is the proof of the Pythagorean theorem using the similarity of triangles.